As already mentioned, both the fitting of Gaussian mixture models and the fitting of k-means clusters are instances of a more general pattern known as expectation maximization, which crops up quite often in unsupervised learning. The general property of problems for which expectation maximization, or EM, as I will henceforward refer to it, are applicable are that the problem has a likelihood which is difficult or impossible to maximize, but that the problem would be much easier if some additional information were available. Of course, it is always true that a problem could be made easier if some additional information were available, specifically if someone just gave you the answers. So this is not a very precise or necessarily helpful definition, but it's a way of understanding the kinds of problems to which it might be applicable. The way to think of it is that the hard problem is a kind of analogue of a much easier problem, but with some pieces missing. So it's an incomplete reflection of the easier problem. As mentioned in the introduction, this can apply to missing data problems as well as latent state problems of the kind that we're focusing on here. The general form of the problem is that we assume we have some measured data, x, and that there is some hidden state which we represent by z, which in some way governs the visible measurements x, and that the way in which that operates is driven by some model parameters theta. We assume we know the form of the joint probability distribution of x and z given theta. The probability of x and z parameterized by theta is the probability of x given z parameterized by theta multiplied by the probability of z, again parameterized by theta. We will assume that we can define these in some way. So, for example, in the Gaussian mixture model case, that first component, the probability of x given z, would be Gaussian, and the second component, the probability of z, would be categorical. These are expressed here just as kind of single probability estimates, but of course these are distributions, and we may well need to marginalize over z to find the probabilities of x. We will do that very shortly. Since we know the forms of these probability functions, we also know the forms of the likelihood function for theta, which would look like this. And we would also be able to form an expression for the posterior distribution of z given x and parameterized by theta. Given all of these expressions, we would be able to calculate some of the variables in terms of others. So if we knew z, we could define a likelihood function for theta and attempt to maximize it. If we knew theta, we could define a posterior distribution on z. Unfortunately, we don't know z, we don't know theta, all we have is x. As in the earlier examples, we will resolve this insoluble problem by just making a guess as to one of the things, then using that guess to estimate the other thing, and then using that estimated other thing to refine the guess, and so on. We can formalize this, as with the GMM example, as two iterable steps. In the E step, or expectation step, we estimate a distribution on z, which we'll call Q, based on our previous estimate of the parameters theta. We then use this distribution Q to formulate the expected log likelihood given that distribution on z. Note that in this expression, the log is inside the summation, so we don't have the problem of having to take the log of a sum. In the M step, or maximization step, we maximize this provisional log likelihood function that we estimated in the E step. We then do that again and again and again until we converge on a solution that we're happy with for some definition of happiness that we choose to make in terms of assessing the models, usually their likelihood. So we've defined here a recurrence relationship between the different components that we're attempting to estimate, but this is a recurrence relation with no starting point. Somehow we need to come up with the initial values, theta 0, which we use in the first E step. As noted in the case of k-means and Gaussian mixtures, this initialization can be pretty important. The optimization is typically non-convex, or rather non-concave, since we're maximizing, and so there is a significant risk of getting stuck in local maxima. How you deal with this initialization problem can vary a lot between different kinds of problem class, but the simple method of trying a bunch of different start values until you get one that works can be surprisingly effective for something very, very crude. So a nice property of expectation maximization is that while it does risk converging to local maxima, it is at least guaranteed to converge to such a local maximum. The expected log likelihood function that we estimate in the E step cannot make things worse. Now this might seem like a rather weak promise, but look around you. So this convergence property for EM is provable. I'm not going to prove it here, but the proof is readily available in the books in the reading list on Moodle. In practice, actually translating any arbitrary model of your choice into the expectation maximization framework, actually framing the computations stipulated by EM, these expressions here, can be rather tricky. There are some straightforward cases, for example, Gaussian mixture models, which is why we present that as an example. But in general, it can be really quite hard. And in practice, it may be more useful to think of expectation maximization as a pattern that occurs regularly as a useful way of addressing problems, rather than a specific step-by-step recipe for solving any particular one. There turn out to be a number of useful and important applications of EM, but it's perhaps telling that these were often developed independently as clever ways of solving a particular problem, using contextually relevant understandings of the problem space, and only in retrospect identified as being a manifestation of the EM algorithm. These applications turn out to all be doing sort of the same thing from a particular point of view, but that's not necessarily the way they are most productively framed in terms of the actual steps being performed.